Now let me solve this confusion between two different ways of writing a regression model I used. I'm pretty sure you were confused, but that was on purpose. Okay, so I use these two notations. Actually, nothing is wrong, both are correct. What's the difference? So in this case, in the first case, you see I use y and x, it's a real measured values, but I also add an error term. Why? Because you will never get data which points exactly line a straight line. They always scatter it around this line, and this scattering is this error term e. Okay. On the other hand, you can use a model and predict y values, so the points will lie exactly on the straight line, right? So in this case, it's not y, it's y predicted. This is why you have this p as a subscript, and then in this case you don't have any error term. Okay. So now you can define what is error. Error, it's a difference between the real measured y values and the ones that model predicts. Okay, let me show you an example. So in this case, I also use people data. X is age in years and Y is income. Okay, so I would like to make a model that will predict an income, average income, for a persons of different age. Okay, so let's model. You can see that we have a model. We have a nice model, not perfect one, but still, it's a red line. And then the model is following. You need to take age, multiply to 130, and then subtract 1156. So that will be the salary, the income, the average income. What's the meaning of this 130? So it means that every time you change x by 1, y will change by 130. Okay? So it's how much of increase in salary you can expect every year, in average, of course. Okay, so you can think that if, for example, in 10 years, you will your annual income will be by 1,000 euro larger. Okay, at least if you are from the same population as this data. So that's the meaning of this. Okay, then look, this is the particular age, right? And this is what we have in our data. So this is true y value. And you can see that it's not exactly on the line, right? But if you, for example, take, let's say it's 33 years. If you put 33 here, you can calculate the y value, the predicted y value. And this is the predicted y value. It's always lying on the straight line, okay? So that's the difference between y and yp. This one is an error of prediction. So this is what models think about your income, or income of this person. And this is the reality. This is what you have in your data, the measured value. So the difference between what model predicts and what you measure is error of prediction. Okay? So this difference tells you how good your model is, how close the model predicts your values to the reality. Now, how to find the baseline? Of course, we need to use this error of prediction to find the baseline, right? So I'll show you a couple of examples, actually 4 examples. So in this case, I have the same data. It's not income and age, it's a different data. And I have different positions of the line. What is the best? Okay. So you can see, for example, the first line, this one, you can see you have only 3 points on the top and a lot of points on the bottom. Probably it's not the baseline, right? So if you start looking at these lines, you can see that sometimes points are more scattered around this line. Sometimes they are balanced, sometimes they are not balanced. So how to find the baseline? So if you combine this together, you can see that probably this one, the dark blue line, is the best. But how we can measure, how we can prove that? Okay, the idea is following. We need to minimize the errors, but because we have error for every point, we need to minimize the total error. Okay, so remember what the error is. Error is the difference between y and yp. So this distance between the points and the straight line is an error, right? So that's the error. It doesn't matter. It's y minus yp and yp minus 1 because we are interested only in magnitude of error. We are not interested in the sign. So it means that we need to square it. So if you square the errors for every point and then take a sum of all squared errors, that will be a statistics to minimize. So if you find a line that minimizes the sum of squared errors, that will be the best line ever. Okay. This way of finding line, it's called ordinary least squares algorithm. So we try to find the least squares possible, the least squared error possible. Okay. So that's just an example. So in this case, if line looks like this, you can see error for every point. And then if you calculate a sum of squared errors, this is what you will get. So in this case, you will get this sum of square root errors. In this case, you will get this sum of square root errors. And in this case, you will get this sum of square root errors. So indeed, this is the best line we got because it minimizes the sum of square root errors. Okay. Actually, luckily, the sum of square root errors depends on the coefficients in a quadratic way. So it means it's a convex. It always has a minimum, a global minimum. So it means that we can mathematically show how to calculate coefficients B0 and B1 that always minimize the sum of square root errors. Okay. So that's the part of this least square algorithms. And I will skip the calculations. I'll just show you the result. So if you want to minimize the sum of square root errors when you make a line fit, you need to calculate the slope as following. You take a covariance between x and y and you divide to variance of x. So that's the way to calculate the slope. And then you can think, okay, covariance, the variance for x, it's a spread for x. Covariance between x and y, it tells how y reacts on changes in x, right? So then you have sort of a balance in between. Okay. And then when you know b1, you can calculate b0 as following. You calculate average of y, calculate average of x, then you subtract y minus b1 times x. So this is b0. This is b0. So in fact, what you need to know the values, of course, and then you calculate covariance, calculate the variance, and then you calculate average values, and then you can do everything actually in the piece of paper. If you want, you can practice with this example. So I have data with 5 points, 1, 2, 3, 4, 5, and this is sum of the values x and y. Then you can see the results. You can see the points and you can see the line best line fit. So if you actually do the calculations, you should find out that b1 should be 1.3 and b0 should be minus 151. Okay, so try to make these calculations yourself.